In recent years, large language models have made remarkable strides in reasoning, thanks in part to reinforcement learning frameworks like reinforcement learning with verifiable rewards, or RLVR. This approach leverages rule-based verifiers to provide binary feedback, correct or incorrect, on final answers. The result? Models learn to generate intermediate reasoning steps that reliably lead to correct solutions, especially in domains like math and programming. But here's the catch. RLVR is limited by its reliance on domain-specific verifiers. These are hard to build for subjective or open-ended tasks, like creative writing, open-ended question answering, or nuanced decision-making. And even when they're possible, they require expert effort and incur high costs. To overcome this, researchers have turned to verifier-free methods. These frameworks use model internal signals, like confidence scores, likelihoods, or consistency checks, to generate reward signals without external supervision. One standout example is RLPR, which computes rewards based on how likely the model is to generate the reference answer given its reasoning trace. This allows training on broad, general-purpose datasets, no manual verifiers needed. Yet even RLPR has a critical flaw. It tends to overfit to the exact wording of the reference answer. The model learns to reproduce the same expression over and over, sacrificing diversity. In tasks where multiple valid formulations exist, such as writing, paraphrasing, or multi-step reasoning, this becomes a serious bottleneck. Enter DARL, diverse answers for reasoning with limited verifiers. Our goal was simple: build a reinforcement learning framework that encourages models to explore semantically equivalent but lexically diverse answers, while still staying aligned with the reference. And we did it without adding any verifiers, extra complexity, or new training stages. So how does DARL work? At its core, DARL introduces a dynamic, diversity-aware reward that adapts based on the model's confidence in the reference answer. Given a question, the model generates a reasoning trace and a final answer. We compare the likelihood of the model producing the reference answer versus its own generated answer, both conditioned on the same reasoning chain. The difference between these two likelihoods is what we call delta, a measure of deviation. If the model is confident in the reference, but still assigns decent probability to its own answer, then delta is small. That means the model is capable of generating a valid alternative, and we reward it for doing so. But here's the key insight: we only reward deviations within a bounded range. This ensures the model explores diversity without straying into incorrect or incoherent territory. The overall reward is a weighted combination of two terms, one that aligns the output with the reference, and another that encourages controlled exploration of alternative formulations. And to make it adaptive, we scale the diversity threshold dynamically based on the model's confidence. When the model is unsure, we keep the exploration narrow, focusing on correctness. When it's confident, we widen the allowable deviation, encouraging richer, more varied outputs. This simple yet powerful design leads to two major benefits: higher policy entropy during training, meaning the model explores more actively across the action space, and higher likelihood assigned to diverse, semantically valid variants, not just the reference. We tested DARL across 13 benchmarks, including reasoning-heavy tasks like GPQA, AIME24, and Theorem QA, as well as general domain challenges like code generation, logical reasoning, and creative writing. The results were striking. On reasoning benchmarks, DARL outperformed RLPR by an average of 1.3 points, with gains of up to 7.03 points on GPQA and AIME24, where multiple valid reasoning paths exist. On general domain tasks, the improvements were even more dramatic: 11.57 points on logical reasoning, 12.44 points on code generation, and 3.35 points on writing tasks. But beyond numbers, the qualitative differences were clear. When asked to solve the same problem, DARL generated responses that were not only correct, but also more structured, readable, and coherent, with standardized reasoning steps and better presentation. In contrast, RLPR often produced verbose, repetitive, or awkwardly phrased outputs, even when logically sound. Why? Because DARL doesn't just optimize for correctness, it actively rewards diverse pathways to correctness. It teaches the model that there's more than one way to get to the right answer. We also conducted ablation studies to validate our design choices. Turning off the diversity reward hurt performance. Using a static threshold was less effective than our dynamic approach. And when we applied DARL to other verifier-free frameworks, like Verifiers, it boosted their performance too, proving its generalizability. Importantly, DARL is fully compatible with existing RL pipelines. It doesn't require new architectures, extra verifiers, or complex reward modeling. It can be plugged into any framework that uses model internal likelihoods as a reward signal, making it easy to adopt and scale. Of course, DARL isn't perfect. It still relies on ground truth answers for supervision. So in scenarios where no reference exists, like purely open-ended creative prompts, it can't be applied directly. But in settings where a reference is available, whether from curated datasets or human annotation, DARL offers a powerful way to improve both accuracy and diversity. In conclusion, DARL shows that explicitly encouraging answer diversity is not a trade-off with correctness. It's a path to better generalization. By promoting controlled exploration within a bounded deviation range, we enable models to learn richer, more flexible reasoning patterns, without sacrificing alignment. This work opens a new direction for reinforcement learning in language models, one where diversity isn't an afterthought, but a core objective. And as we push toward more open-ended, real-world applications, the ability to generate multiple valid, high-quality responses will be essential.